Thank you, John, and good afternoon, everyone. My name is Doug Rose. I'm Vice President of Technology Strategy at SunPower Corporation. A couple quick items on my background. I've been in PV over 25 years, first at NREL, then First Solar, then SunPower. At SunPower, my first role was as the product engineering manager for the first solar cells we took into mass production. Then I was in charge of the development and launch of our modules and then improvement of those. And then I went into a broader role, and in that role, one of the functions was assessing new technologies. A preview of what I'm going to talk about today. The topic is crystalline silicon PV, and that was 95% or so of the more than 100 gigawatts of PV that was shipped and installed last year. So this is obviously a very broad topic. So I'll try to give you the overview of it and give you some ideas of how you can delve deeper. The global prices of PV have dropped tremendously over the years, according to PV InfoLink, and this is supported by some other sources. Standard multi-crystalline module last year, an average one was about 22 cents a watt. That's in bulk. And a monocrystalline PERC module, a couple points higher efficiency, 28 cents a watt. There is more technology variation than just multicrystalline or monocrystalline. I'll give you a quick overview of some of those technologies. Even separate from the cell approach, there's variation in module approaches and materials. The leading PV companies now are very large scale, some of them over 10 gigawatts per year, or they have differentiated technologies. So they're not trying to sell the same thing as the vast majority of the producers, so they can compete on more than just price. The goal of this presentation is to provide an overview of the silicon PV industry, but also some public sources of information so you can delve deeper or stay up to date over time. SunPower is a public company, so I'll give just a quick safe harbor statement. I don't intend to give any forward-looking statements about SunPower. If I do, standard caveats apply. Anything you do act on is at your own risk. Good news, big picture. PV is winning. It's really remarkable how far this industry has come. Last year, there was more than 100 gigawatts of installations. BNF is saying 109 gigawatts. For comparison, if you add up the natural gas, coal, and nuclear combined, there was an added about 100 gigawatts of capacity. And in more and more locations, PV provides the lowest cost of energy, with some of the big PV utility plants having a levelized cost of energy of 2 to 3 cents per kilowatt hour. This chart just shows the growth over time, and it breaks it down by country. This is the first example of some detail that I'll have in this presentation that I won't have time to talk to. So don't feel like you have to catch everything of each of these figures. It's provided, so if you go back in and look deeper, it's there for you. First, starting materials and something on terminology that can be very confusing from people outside the silicon industry. The starting material is called poly or polysilicon. It's made with big chemical plants that go through and make trichlorosilane, then they make it into rods and break that up into chunks. And that's called the poly or polysilicon. There's two things that you can do with that material. The vast majority of them are done one of these two ways, which is to grow either a single crystal ingot from Czochralski method, cut it into bricks, and then use wire saws, which simultaneously cut 4 of these bricks into hundreds of wafers all at once. Alternative to the single crystal, you can take it and cast it into a really big ingot. cut that ingot up, and then do the same thing. Wire saw that into individual wafers. These wafers and the cells that are made with them are often called multi or multicrystalline, but they're also often called poly or polycrystalline. So keep that in mind. If somebody says poly, they could be talking about the starting material, or multicrystalline cells or wafers. On the cell terminology, you'll hear the term PERC a lot, and that's the passivated emitter and rear cell. It's taking the process for the old standard of aluminum back surface field and adding a couple of steps, typically 2 or 3 steps, of a rear passivation stack on the back. And that reduces recombination and also provides an infrared reflector on the back. It adds a point or so of efficiency. There are variations within that. Some for their top class of module can add 2 to 4 steps on the front side to improve that surface. And if you lump all of the PERC variations together, it is now the most common technology out there, going from practically nothing in 2015 to over 50% today. Here's a few more of the types. Instead of just passivation, you can diffuse in, and that's a PERT. You could locally diffuse those for even higher efficiency, that's a PERL. Or you could use a tunnel oxide and a silicon film to dope it. It's also called a polysilicon film, as if it wasn't already confusing enough. And then there's a variety of things that you could do on the front side. And then lastly, there's something called heterojunction. So instead of the PN junction being within the material, it's at the surface. This one is a front contact approach, which is the most common type of heterojunction by far. And then lastly, there's an interdigitated back contact structure. And that's what SunPower uses for our main product, abbreviated IBC. There is variations within this as well. You can use passivated contacts. You could even use heterojunctions for the contacts. The first public source I'm going to point out to you is this one, the International Technology Roadmap for PV. This is the 10th edition of it. This is from a presentation about it. So they've been doing this for 10 years. It started out through one of the standards organization and now has been transitioned to a PV equipment association in concert with the DNV, which is a big testing organization, and as contributors, many people from different companies around the world and some institutes. And both the full report and where these slides were from, the presentation, are available at the vdma.org website. This is one of those slides with some really great data. The first thing is, this is the learning curve, where you just plot the average price versus the cumulative volume installed. And going back decades, it's been at a learning rate of 23%, meaning that when you double the installed capacity, you get a 23% reduction in price. And they note that over the last 10 years or so, it's been an even faster learning rate, about 40%. They also say that last year, the average price was about 24 cents a watt, and they break that down into the constituents of it, the module contributions, cell, and then wafer and polysilicon. There's a bunch of other information like the price evolution over the last few years, including by component. And if you look at the learning curves, one of the most useful things you can do with them is to project forward. There are decisions that you have to make. There's some assumptions. Do you assume that, well, we're below the learning curve now, so there's a reversion to that point? The entities that have assumed that over the last few years have been very mistaken. Or do you assume that this accelerated learning curve continues. Here's an example where I'll take the kind of a middle road, say that it's the 23% learning curve, but we're going to start with last year's data point, and we'll assume a growth rate for volume of 10% per year. And the growth over the last 10 years has been more than 25%. There are projections for future growth anywhere from 0 to 25% or more that I've seen. But with these assumptions, what you see is by the end of 2022, a terawatt installed at an average module price of 19 cents a watt. And the end of 27, 2 terawatts, an average price of 15 cents a watt. There are even assumptions, though, in terms of, well, instead of 15 cents a watt, should you start with the higher priced, a little better modules, and so instead of 15 cents, it's 20 cents, but they're much better modules than today. The ITRPV has great information on what there is today and the projections going forward. So bottoms up details. This one is looking at how much is mono and multi. They say more than half is mono now, and then over the next 10 years, 90% of it is mono, with about split between P-type and N-type. Some analysts show an even faster transition to mono and N-type. There's information like this: how much grams of polysilicon are used in each wafer, and you could then use that to convert to per watt. There's things on silver. Silver is used in most crystalline silicon PV to make the metal collection grid on the cell. The report shows that heterojunction on average has about double of what a P-type is. But here's a good time to point out that not all technologies are represented by this full aggregation or even the way it's divided up. SunPower's IBC uses no silver at all. It's a copper approach. There's information on module materials. A backsheet is the back part of the full module. Glass front, about 10% of modules have a glass on the back. Most of them have some type of foil, usually a multi-layer foil that's of polymers. And you see the big variety of approaches and the forecast of growth of some of those approaches, such as the polyolefin is the one that's predicted to grow the most. There's information on equipment. I'm going to use this to illustrate how far the industry has come and that continued progress is expected. When SunPower built our first plant for mass production 15 years ago, a little over 15 years ago, the tools that we used were typically about 12 megawatts per year, meaning one tool for one step could put out enough for 12 megawatts. If you look at the average here, if you take into, there's different types of equipment here, some of the metallization, thermal, wet, but 6,000 is a middle point here. Take the equipment effectiveness and some other assumptions, and you get now for equipment of 230 megawatts, so 20 times as much. And if you project forward 4 years by this, that increases again to over 400 megawatts. So only 2.5 tools used for one step for a gigawatt factory. With any source of information that you get, it's really important to look at how have the projections been in the past. You see some, like the EIA's projections for growth of PV, have been ludicrously bad. They almost always forecast almost no growth. They've been wrong every single year. Obviously, don't pay any attention to them. ITRPV has taken that approach to heart, even for their own. They want to see how their predictions have been. These two charts are from their report, and on the finger width, the projections have been very accurate. So in the first report, they said that they would decrease like this over the next few years, and then each subsequent report, it's been right on that curve. Whereas on a wafer thickness, that first report projected fast reductions in wafer thickness. For some variety of reasons, the biggest being that polysilicon got cheaper, so there was not the reason to drive it as hard, and reliability became more important. The thickness stayed well above those early predictions and even the middle year predictions. But it isn't always conservative. Here's a case where the progress was very much faster than what was predicted. Back in 2016, there was a projection of moving from a slurry-based wire saw to a diamond wire saw for multicrystalline being pretty hard. Forecast to not change much over a few years and then slowly go down over the next decade. The next year, well, actually progress was slower than anticipated, but there was the belief that these problems would be solving, and so it was projected to accelerate a little bit. The next year, look at that. Progress occurred actually much faster than expected. And then this year, essentially they're saying at the end of 2018, it's all transitioned to diamond wire. And that was because of progress in etching wire saws and the diamond wires, but also that it didn't have any complexity to downstream. Significant complexity at least. There wasn't a big reliability concern from the customer side. Another source of information that you can look to is something called PV InfoLink. They post data on the constituent prices, polysilicon, wafers, cells, modules, and I looked at this today, and they have the average polysilicon price being below $9 a kilogram. A huge contrast to when it spiked many years ago at $400 a kilogram. That gives less than $3 cents per watt, US cents per watt for the poly. They have the prices of the wafers, and you can convert that into cents per watt. It's about 7 cents. For cells, they sell for 16 cents a watt. So the price to go from the wafer to the cell is less than that, and I'll show you an example there. And then modules, they have at 22 cents a watt for multi, 27 cents a watt for mono, so that agrees with ITRPV. But they give more color on, even though that's the average, in the US, the average is 38 cents a watt. And that's because of tariffs, but also higher channel cost, and the fact that the better modules are more highly valued in the US. More quality conscious customers and some applications that really value the better products. And in fact, the high efficiency in mono can be far, far above that 38 cents a watt for certain market segments. So here's that step value that I mentioned. If you subtract the module price by the cell price, you see these steps, and the value add is for those commodity ones is on those levels there. Since polysilicon is so important to future projections, will poly go way up? What would that do to the cost of crystalline silicon PV? Well, it was so high, there was such a spike because the companies that made poly, they made it for semiconductor industry, didn't believe in solar. And so they didn't expand near enough. And it was new companies that came in that built the factories and then figured out how to build them much cheaper, that drove the volume and the cost and price reductions. Dacho New Energy is probably the low cost leader. They give the details of their production cost of being below $8 a kilogram last quarter, and that includes depreciation. And then they also tell their average price over the succeeding quarters. And you can see that about a year ago, there was a little bit of a spike to just below $20 a kilogram, and it's come down again since. There are other major producers, some of the biggest ones in China, but also in Germany, Korea, and the US. Contract prices can be higher than these average costs that a company is selling at now because an off-taker may have gone in at a time, signed a contract when it was higher, or they just want to make sure they know their price over the next years so they can forward price their modules as well. And the LONGi had one of their contracts is implied just above $15 a kilogram. This point is really important. Polysilicon Capex used to be really high, and it was one of the reasons given for how can crystalline silicon be the solution to the world's need for PV, because it was so expensive to build new capacity to grow. You couldn't have enough profits to do it. But that has changed. Instead of 80 cents or more per watt of, and you can convert it to how much is it to build a certain dollar per kilogram, and then you convert that into how many watts does that produce. It's now down around 5 cents a watt. So that's not an impediment to growth. And if you look at the next step, at one point, mono ingot was very expensive by announcements from LONGi. That's no longer the case. They gave their announcement for 12 gigawatts of expansion. It was below 5 cents per watt capex. And wafering is even less, a little over 2 cents per watt capex. And so then if we look at the cells and modules, cells, there's a big range from below 10 cents per watt to LONGi's in Malaysia. They reported at 12.5 cents a watt. And then modules, an even bigger range, from close to 1 cent a watt for a semi-automated in China to much higher for something like in the US that is completely automated, as I'll give an example on that. But if you add up all these, it's below 30 cents per watt, which is not an impediment for pretty rapid growth. I showed the average efficiency for those modules. Just a reminder that you'll hear announcements for what cells are, and module efficiency is always lower than cell efficiency. And the reason is mainly because the module area is bigger than the sum of the area of the cells. You have to have some gaps around the edges of the module. The frame takes up more space. There's tiny gaps between the cells. And generally that reduces something like a 21 cent a watt, 21% cell down to around 18.7%. There can also be a difference in the sum of the cells versus the module power, but it's pretty close. Generally around 100%, depending on the technology type. And part of that is, in addition to the losses like mismatch and series resistance, there's gains. And the biggest one being light that goes around or between the cells can bounce off the backsheet, be internally reflected at the glass air interface, and be recaptured by the cells. And then there's the, in many cases, even bigger difference between a champion cell that's announced and a full-sized production cell. That this was an article that just went through some of those things. It can be really remarkable with somebody using processes that are completely unsuited to production and smaller area and a bunch of things, and they'll announce a 25% cell, but their production is far below that. Whereas other technologies, there's not a big gap between them. Efficiency is valuable because it reduces the area-related cost, but it also reduces all the fixed cost on a dollar per watt basis for any situation where you have area constraints. And in some applications, that can be the even bigger drivers. There's a lot of sources for what are efficiencies of modules running. This is one from a report by Taiyang News. Here's another source of information. They put out reports, they have news, and this was one from last year where they looked at the top bin for this size of module, and said that SunPower had the highest efficiency at 22.7, on down to generally a little below 20% for the ones running their best mono PERC, but also Panasonic's heterojunction, but LG being the second, and I'll talk more about them. The module technologies, huge amounts of information on that if you delve into it. Different ways of interconnecting, even using conductive adhesives instead of solders, full cells, half cells, strips of cells that are then tiled, different approaches to materials in monofacial and bifacial. If you look at these news sources, you'll see some posts where somebody will report on one of the shows. This was one from PV InfoLink about one of the big expos in Tokyo, and it's almost as good as walking around the floor. They give examples of, well, for shingled modules, here's the companies that they saw doing it. Here's the type of cells, the wattage. It gives you a good sense of what's out there. And bifacial is one of the things that's out there. The growth has consistently been less than what companies have said was going to happen, but there are more large arrays that are being put in, which should give the good data that will justify more going in. Bifacial works by light that gets reflected from the ground or directly or from diffuse light that hits the back of the module also contributes to the production. One of the things that has kept it from being as good as some people were claiming it would be is sometimes you have to do some things to collect that power. Here, long G, when the tracker supplier spread the modules, so there isn't shading from this torque tube. They can have to do things for the module to make them suited to that. You can have to do things in ground prep to prevent there being non-uniformity. But in time, there will be more and more applications that use it. There is a report in Tying News. They go through all the different architectures of cells and the companies working on them. Reliability. There could be and is entire conferences devoted to recent reliability work. NREL sponsors one of the very good conferences on that. It's a workshop. And overall, crystalline silicon has good reliability, but there is variation. Typical warranty is for 15% total power degradation over the course of 25 years. But there's a range from great warranties to some that have terms that make them pretty much worthless. But that's becoming less common. There is variability in the performance themselves as well. It's not just the warranty. This is from a report from DNVGL, where their test showed that here's a case of one manufacturer and one module type, but a different bill of materials for each, with completely different behavior in the accelerated testing. There is really good technical literature on reliability as well. So you can go see things like the light-enhanced temperature-induced degradation and how it was a huge problem for PERC cells, but has mostly been fixed, and in terms of accelerated tests, completely been fixed, and possibly there's just a little controversy, but the majority believe that this does completely address it. There's a lot of good information as far as reliability approach. Take a look at those conferences. This is one that I presented years ago at an InterSolar, where you have the design for reliability. You have to have the materials and the approach that results in reliable module if it's made right. And then you have all the manufacturing quality aspects to make sure it's made right every time and get learning from closed loop learning over time. And now I'm going to quickly go through some of the key companies that are out there. There are other ones that I could have put on this list, but I wanted to give a sense of the big companies or the leading differentiated product manufacturers that are out there. This is a list of the largest module manufacturers from PV Tech, with Jinko Solar being the largest. And the top 4, including Canadian Solar, are all Chinese companies. And number 5, Hanwha Cells, is a Korean company. Cell manufacturers, the largest ones of those, there's a lot of mapping from one to the other, but it's not complete. The biggest exception being Tongwei, which doesn't make much modules, but as of today, or at least by the end of the year, will be the largest cell manufacturer in the world. And that's a Chinese company as well. Then there's the larger of the companies that make a product that is very different, a premium product relative to the standard product. SunPower, LG Solar, and Panasonic are the most well-known. But a lot of companies are working to have at least a portion of their capacity that is within that very differentiated product. REC Solar is putting in a heterojunction line, which they hope to get them into that realm. Tesla is seeking to have that very differentiated product through the use of a different approach to the module itself, using, now they're in cooperation with Panasonic of making the cells for that in the factory. I'll go ahead and talk about SunPower first, take the presenter's prerogative, and point out that really SunPower now is 3 companies within a company. The downstream parts of it, North American residential and North American commercial, are leaders in their respective channels. Leader in market share for commercial and 250,000 customers for residential. And both of these channels do full systems and storage as well. And then SunPower Technology is the module manufacturer, cell and module manufacturer that should be compared to some of the other ones that we're talking about here. Our core product is that SunPower IBC. Better aesthetics, better reliability, that copper foundation, and we have a little bit of a new niche product of a flexible, lightweight one. The architecture is based on having the metal on both for the N and the P on the backside, with a front surface that can just be optimized for getting in the light and not allowing the recombination of carriers at the front. This is our history with this product, going from 21% in production back in 2004 and increasing a little bit as we went to succeeding generations, and increasing in the production throughput to now 25% with 10 gigawatts cumulative. And the latest step is more about cost reduction. It's going to a larger cell. The previous 3 generations were smaller cells than the standard cells. It was SunPower and Panasonic. That increased costs. The latest generation, that is not the case, and it uses the latest larger equipment as well. In addition to just the modules, we have some things like built-in microinverters, making it an AC module, and systems, and that includes things like monitor. Reliability is core to SunPower's value proposition to customers. There's third-party tests showing less degradation than conventional panels and much lower failure rates. And that was backed up by long-term reliability testing. And I'm going to use this not only to show the good behavior that we've reported, but also the variation within the conventional panels. And this is from literature and others testing. The certification standard is only 200 thermal cycles, but most studies now are indicating that around 800 thermal cycles is actually representative of the full life. And this is a test out to 3,000 for SunPower's. There's also long-term humidity testing with this variation and long-term humidity freeze testing with variation and worse performance in the conventional panels as well. And then lastly, SunPower has another product line that we got from acquiring a company that had a technology for cutting the cells into little strips and assembling those into a package that has a little higher efficiency and is more reliable because it takes out 2 of the common failure modes. And other companies now make this type of module, but SunPower is by far the largest producer of them, particularly with our partner. And we're also ramping that in the US, in the Oregon facility. Jinko Solar is the largest manufacturer of modules in the world. They shipped 11.4 gigawatts last year. Now, they only had 10.8 gigawatts of module capacity and only 7 gigawatts of cell capacity, which shows that, like a lot of the other leaders, they didn't make all their own products. There were some that were made either under their supervision or for other means that then went out as Jinko modules. And it's been a business model that has worked well for the companies that managed it well. And a revenue last year of over $3.6 billion and additional growth planned. They just opened a 400 megawatt per year module plant in Jacksonville, Florida. And you can look at some of their other press releases. You see this one from another one of their plants. Look at that level of automation. And this is just handling the modules at the end of the testers with all these binning racks. This just shows a sampling of their module types. They have a whole bunch of module types. When you're making that much product, it makes sense to try to have products that are suited to different applications. And also, a lot of those companies have some older process equipment. And as long as you could run it profitably, it doesn't make sense just to scrap it. So you do end up with some of these products like an old polycrystalline module with the low end of just over 16%. On the high end, they're half cell mono PERC. Highest is getting close to 20% efficiency. LongG is the next one to talk about. This is another one that is a very significant company, but their branding isn't as much. You don't see as many of those modules in channels and residential in particular. They're the largest manufacturer of mono wafers. It's LongG and a company called TZS go back and forth of which one has the most capacity. Both of them are growing very fast. And they have, according to this estimate, planning on 6 gigawatts of cells by the end of next year. But the LongG website says that they already have 8 gigawatts of cells. Generally, when there's a disagreement like that, it makes sense to look for other sources that could figure out which of those is correct. Hanwha Cells is the Korean company. They had acquired a company in China quite a while ago. They had a partnership, and that gave them some of their capacity. But it's all over the world with 8 to 9 gigawatts and then module capacity a little above that. Hanwha is a giant chemical company, and they also make some of the materials that go into solar panels and do some of the project development. I'm going to use this statement to point out that you can't take any company statement, even an analyst statement, as correct on its own. don't mean to pick on Hanwha here. I don't think that they're any worse than in other companies, and they're much better than some. But they had a press release that said that their 1 gigawatt cells were the world's most efficient cells. That was not true. But it may have just been a case where that there were qualifications to that what they meant to say was of that type or of a certain production approach. So you get anything from a little bit of unstated assumptions to intentionally misleading from some companies. So anytime you see something, you have to dig in a little more. This month, or it was actually last month, Hanwha made a lot of press because they sued some other big companies that make PERC cells, saying that they infringe upon Hanwha's patents for PERC. Those companies have disputed those claims and have said that the Hanwha patents were for atomic layer deposition, aluminum oxide, but those companies put it down by PECVD instead. Hanwha is the company that put in the largest U.S. module manufacturing. They say it will be 1.7 gigawatts per year when fully ramped. High Capex, according to what they announced. They also say that it would be 600 employees when ramped. If you assume 30,000 an employee, it's in Dalton, Georgia, that's only a cent per watt for the labor. They have a range of products as well. On the high end, their best half cell mono PERC with 6 bus bars. On the low end, 16% polycrystalline module. Canadian Solar. And they were one of the largest. They've dropped down to fourth place there. They produced a little fewer, 6.6 gigawatts in 18 compared to 6.8 in 17. They had to retool their approach. They had some older polycrystalline lines. They have a higher revenue than you would think from that production because they also had some downstream work as well. Hanwha, there's the biggest solar company you may not have heard of. In 2016, they only had 3 gigawatts of cell capacity. Now, it's probably around 12 gigawatts. And it may double again in the next 3 years. And the capacity for that is mostly mono PERC. But they have a pilot production of heterojunction. They are also putting in capacity to make that starting material, the polysilicon, with plans to become one of the major players by the end of next year. And they're guiding to being profitable as well. LG Solar. LG it's not as easy to triangulate on the how much capacity of each type. I'm guessing around 1.6 gigawatts, so their NPERT TOPCon, that's the passivated contact, and maybe 150 to 200 megawatts of IBC, plus they might have some standard. They're building a 500 megawatt per year module factory in Alabama, and if you look at their product catalogs, the Neon 2 has the top bin of 19.8%, and they go through some of the things that they do to get that higher efficiency. The wire technology instead of bus bars, highly reflective backsheet, double printing of silver, and several other things including those passivated, to get that efficiency up around there. It's not as high as the SunPowers in particular, but it is above most. They do have one product, and this is the 150 to 200 megawatts by my estimation, that is closer to SunPower efficiency, with the top bin being over 21%. This is an IBC approach, and so it doesn't have the metal on as well. So in summary, It is really, it's exciting. For those of us, whether you're new to this industry or you've been in it a long time, it's really exciting seeing that PV is having such an impact. It's the lowest cost energy option in some places, and the installed capacity is already over a half a terawatt. Crystalline silicon PV shipments are now around 100 gigawatts a year. That's about 95% of the PV market. The average price of those multi-modules, about 22%. And the prices, though, are higher in some countries and for higher efficiency panels. So if you're trying to get a retail, small quantity, high efficiency N-type panel for your house, you're not going to be paying 22 cents a watt. You will be paying above that. But even well above that, for most homeowners, it results in a significant savings on their power bill. Monocrystalline is now more than half of the market, and it's growing fast. The full value chain Capex is low, remarkably less than 30 cents a watt, likely, for mono-PERC in China. And the biggest manufacturers have over 10 gigawatts of capacity. And SunPower and LG Solar are number 1 and 2 in US residential. Here are some of those free information sources that I drew heavily on for this. You can also look at technical literature, but one thing you should be careful of, if you look at technical literature for things like prices and costs, generally significantly lags what's actually happening in the industry. That they'll reference some study that was done by somebody that wasn't in touch with what's really happening in industry, and it's just completely out of touch. These sources can give you much better information. I found that the best way to create an understanding of what's happening and what is likely to happen is to combine an understanding of the technologies, and the technical literature is the best way to do that. But some of these studies from these sources can also be very useful. You put that with this recent information from all these sources, and then add in some of the other sources of information that aren't as available, you have to pay money for. There's several organizations that have subscriptions for more information. They have their own analysts. But also getting out there and talking to people can be one of the best ways to understand what is and what will be. So thank you very much for your attention, and it looks like we have a few minutes for questions.
Thank you so much, Doug. If anyone has any questions, feel free to either type them into the chat window, or you can enable your microphone and ask that way as well.
While we're waiting on somebody to type something out, I'll add color to a couple of the things that were in the presentation. One is on heterojunction. Heterojunction has great potential. You have to be careful in the history of how difficult it is to take it from a champion cell into an average production. There have been companies that have announced that they're going to take something into production and then had difficulties with that. Solar City was probably the biggest splashy example of that, but there have been others. But I think the technology has come along since then. There is a diffusion of knowledge that could contribute to that may change that track record of taking it to production. A question is Tong Wei. Do you expect we'll see other Chinese companies expand rapidly like that soon, or has there been consolidation there? Excellent question. There has been some consolidation. The low-scale, smaller companies have generally gone away and couldn't afford to keep up with the generations. Those companies went away. There are a couple of new companies that may join Tongwei with that, but Tongwei was an extremely well-funded company with a lot of support from local and national governments. So it's hard to reproduce fully what they have done. And it's even harder to reproduce success downstream. That's why Tongwei's been pretty smart of going after the aspects that can be commoditized so they can best use the standard equipment out there and not have to develop channels. Question is, how would I account for the Chinese government support for their manufacturers? It is an important part of it, but it's often overstated that the land is often free, but the equipment is readily available at low cost now. And the knowledge is out there. And those companies, the fact that the companies work together is probably more significant. In any event, those costs are real. It's not just a matter of the Chinese government supplying them all free equipment and free labor, that kind of things. It's like we're going to be getting a question here from Brendan. Looking forward to seeing this question. I thought it would be this. What do I think about the future of perovskite silicon tandems? For instance, Oxford PV. I could make a strong case in both directions. I definitely don't believe the commercialization will happen anywhere near as fast as the proponents have been saying. The time it takes to understand whether something is going to be reliable, solve all the problems that would affect that, and then convince customers of that can be a very long time, except for things like if you're making it for drones or something that is high efficiency and doesn't need to last a long time. The problem is with silicon getting so high efficiency at low cost, when you can have a 25% efficient cell with costs just a little above standard, it makes it tougher for a perovskite silicon because with a tandem with silicon at the back, about 2/3 of the power needs to come from that top cell. So it has to be very good quality. But perovskite does have some unique properties. The ability to get the low recombination is remarkable for that type of material. And as problems are solved, if those products can find the right niches to then expand, then it could be in a situation where it's piggybacking off of the success of silicon, of having really low cost wafers and the bottom cell.
Yeah, I think I speak for everyone in echoing Brendan's comment. Thank you, Doug, for the very thorough answers and for the talk. If there aren't any more questions, I think we won't take up any more of his time.
Goodbye.